Hello. Hello everyone. Today we will continue to look at the content of HCI storage. Previously, we have already introduced the data storage content within solid-state drives as a whole. Next, we will specifically look at each unit and its specific function, and the relationship between them. First of all, the main content of this lesson is about the data relationship of our flash memory chips. Flash memory, as the most critical part of our current storage technology, is mainly used in our solid-state drives and other storage devices like USB drives. Next, we will specifically take a look at the data relationship of flash memory chips to help everyone understand the principles of storage and the issue of optimizing storage performance. First, let's look at the smallest unit. On the left, this is the smallest unit. In our flash memory, our cell is like a tiny warehouse used to store our binary data. Let's take the cell mentioned here as an example, okay? Here it's every 18,336 multiplied by 8. Logically, these cells can be configured to form a page. The number here is quite large, but just understanding it is enough. You don't necessarily have to remember this number. Here, this is essentially its basic composition, with the smallest unit being a cell. Starting from a cell, there are a total of 146,688 cells. These cells can be configured to form a page. This is equivalent to combining many small storage units, according to certain rules, to form a larger storage area. This configuration is actually a larger storage area, which includes 146,000 cells. This is the relationship between them. Here, the storage capacity of a cell is the most basic, and it determines the flash memory's basic storage density and performance. Different types of flash memory, such as the SLC single-level cell, multi-level cell, triple-level, and quad-level cells, which we introduced in the last lesson. Among them, the number of data bits stored in each cell is different. For example, as we mentioned in the last lesson, SLC, it stores 1 bit of data, which results in the advantage of having a very fast read and write speed and a long lifespan. However, the downside is the cost is relatively high. Then when it comes to TLC, for example, TLC stores 3 bits of data, which significantly reduces the cost, but the read and write speed is relatively slower, and the lifespan is also somewhat reduced. So, as we summarized in the last lesson, right? From left to right, actually, it means that the speed gradually slows down, the lifespan gradually shortens, but the cost also gradually decreases. This is one of their basic characteristics. So this is the basic situation of our cell. Next, let's talk about the second configuration. The configuration is first composed of 140,000 cells. That's the first point. The second point about the configuration is that it is the smallest unit for reading and writing within our flash memory chip, and also the smallest I/O unit. Each configuration can store 16 KB of content, along with 1952B of error correction code data. This error correction code is actually very important. It's like a data bodyguard that can detect and correct errors that occur during storage or transmission. For example, when we use a USB drive to transfer files, if the data is in flash memory. If there is a shift or a few bits of error, our error correction code can use our verification algorithm to detect and attempt to correct these errors. This ensures that the data we ultimately receive, read, or transmit is accurate and error-free. This is a primary function of our configuration. Moving on to the next step, our block is first composed of 768 configurations. Yes, 768 configurations make up one block. A block is the smallest unit of erasure or programming in flash memory. This means that when we perform data writing operations on flash memory, we need to modify a configuration data. Here, due to a characteristic of flash memory, we cannot directly overwrite data. Instead, we need to do something else. What does it mean to erase an entire block first? It means clearing out the entire block completely and then writing to it. This is one reason why the write speed of flash memory is relatively slow. The write speed, relatively speaking, is because it doesn't write directly or overwrite directly. Instead, it first erases, clears the original data, and then writes new data. This is our block. Going up one level. 1478 blocks can form a plane. A complete flash chip is mainly composed of two areas. One area stores blocks with odd numbers, and the other stores blocks with even numbers. In the end, there are two. Pay attention, there are two. The planes are multiplied by something to form a whole. One records odd numbers, and the other records even numbers, divided into two parts. These two planes can operate in parallel, and this parallel operation can improve the read and write performance of our flash memory. It's like having two factories, two production lines working simultaneously, so naturally the efficiency will increase. This is the main function of a plane. In practical applications, when our solid-state drive reads data, the two planes can simultaneously read data from different blocks, effectively doubling the data speed. The data speed is directly doubled. This is the composition of one of our blocks. In addition to this, we also mentioned earlier the concept of ECC, which is an error correction code. This error correction code is mainly used in flash memory storage. It mainly serves the purpose of addressing the issue. That as the number of write and erase cycles increases, the storage performance of our cells will degrade, and the probability of errors will increase. At this point, the error correction code becomes very important, as it can effectively reduce the occurrence of errors. This is the main use of our error correction code. The main use. From the perspective of storage device performance, the data relationship of our flash memory chips can actually affect the overall performance of our devices. For example, the design of our configuration and block size will affect our read and write speeds, as well as storage efficiency. The smaller the configuration, the higher our read performance will be. However, it will increase the number of write operations. So what if the block size is larger? Well, this can improve write efficiency. However, when modifying small data, it may cause unnecessary erase operations, which in turn can affect the lifespan of our flash memory. Therefore, in the design and manufacturing process of flash memory chips, various factors need to be considered, such as optimizing configuration parameters like block size, to achieve an optimal balance between performance and lifespan. In actual flash memory applications, wear leveling technology comes into play. This is because the number of erase cycles for our flash memory is limited. Why? For instance, if your flash memory reaches the maximum number of erase cycles, then your solid-state drive will frequently encounter issues such as the errors we mentioned earlier during the transmission process. In such cases, if the errors continue to increase, this actually becomes an irreversible problem. Even with error checking, it can't be completely verified, because if there are too many errors, the overall effect is already equivalent to reaching the end of its lifespan. So everyone should definitely pay attention to this. The lifespan of a solid-state drive mainly depends on the number of erase cycles. For instance, if you've used it for a long time, but don't frequently erase data, then in such cases, the lifespan will actually be longer. But if you frequently erase data, then the lifespan will actually be shorter than expected. This is an issue of wear and tear, shall we? A problem of wear and tear. Well, wear leveling technology actually uses algorithms to evenly distribute the erase cycles across all the blocks. This way, each block shares the erase cycles equally, which extends the overall lifespan. It helps prevent situations where only one block fails, thus minimizing such occurrences. It's like a car, right? You can't just use one tire if one tire wears out, right? The other tires can't be used together either, and you need to replace a tire. It's the same principle here. This is the basic relationship of our flash memory chip data. If you want to learn Washington technology or obtain the Washington question bank, please send me a private message. I can also leave more comments below the video for technical exchanges. Alright, let's stop here for today.